Welcome to another episode of the ASEF Podcast. I'm Tanja Janko, host of the Science Vertical, and today we are joined by Simon DeDeo, who is a complexity scientist and whose work explores how meaning, reasoning, and knowledge emerge in social systems. Simon holds a PhD in astrophysics and is currently a professor in social and decision sciences at Carnegie Mellon University and is an external professor at Santa Fe Institute. Simon's research sits at intersection of physics, computer science, and humanities, and focuses on how patterns become explanations and how humans move from observing the world to understanding it. Thank you very much for joining us today.
Thank you, Tanya. It's a pleasure to be here.
So first, I would like to start with your background. So you were doing theoretical astrophysics and then you moved to humanities. What was your reason for change?
There's an old joke. There was some famous bank robber in the United States. He robbed banks. He was great at robbing banks. And at some point, he finally got caught and he was sort of a celebrity. And so they interviewed him and they said, "Why do you rob banks?" And he replied, "That's where the money is." And so we were all, when you do something like physics, particularly as an undergraduate, it's a very intense subject. You have like a core group of people that you kind of survive your major with. And, we were there because that's where we thought the great problems were. We were excited to be, we were like Oppenheimer, man. It was awesome. It was really exciting. A lot of books had come out. Like I cut my teeth at 12 years old reading Brief History of Time. It was one of the most exciting things I had encountered, even more exciting than Isaac Asimov. Brian Greene came out with The Elegant Universe, right? It was this moment in the late 90s, early 2000s where it felt like we were on the verge of cracking these really amazing problems. And that never happened. Somehow the ideas that we thought we were going to be able to work on, the kinds of questions we were going to be able to ask, it never really happened. Something kind of went wrong. Sabine Hosfelder has written about this. Lost in Math is this wonderful book about the ways in which physics, or at least the way we were pursuing physics, kind of failed us. And God, I've never really said this actually, sort of in public, but yeah, we were really excited. And as time ground on, the LHC turns on, for example, the Large Hadron Collider turns on, and they discover the Higgs boson, which in the popular press was extraordinarily exciting, and it was a great human achievement, well done, Homo sapiens. But the Higgs boson was something I learned about in my master's program, right? This was old physics from the point of view of a theoretical physicist. I was nearby some great observational astronomers, observational astrophysicists. They were doing what was called the cosmic microwave background. They nailed it, right? They completely nailed the fundamental parameters of the universe. And we were left with these mysteries that were deep mysteries that we just had no handle on. We didn't have a good way to approach them. And so a lot of us left. Karina Curto, we did problem sets together back in the day. Karina went on, she did her PhD in string theory. It was her copy of Elegant Universe that I was reading, right? She's now a neuroscientist. Doing, in one sense, of course, you never escape your training, right? So the way that she studies neural networks, the way the brain works, very inflected by her time in physics, and the same for me. But yeah, it was this diaspora where a lot of us started leaving. And, no one rage quit physics, right? But we just all of us, I think, started encountering problems in other disciplines that sort of reminded us why we got into physics in the first place. There's still great physics to be done, and there's still amazing physics that we're doing, but I mean, if you think about like what's your problem to person ratio, right? Physics has the United States. I don't know how many physicists are in the United States. Like let's say 100,000. There's 100,000 physicists in the United States. Theoretical physicists, let's say even smaller number, but we have 4 problems. Like there's like 4 problems. When you go to study, if you move, let's say, to neuroscience, as Karina did, or you move into the social sciences and the cognitive sciences, as I did, like we have more problems than people, right? There are so many good problems for us to attack, and yeah, so I started working at the Santa Fe Institute. I mean, I was hired there as a postdoc, in part because I had a record as a physicist, but also because I was open to new kinds of problems. And I never looked back, so that was maybe, it's 2026, so that was maybe 15 years, no, maybe 17, 18 years ago that I started that move. And I built a career on a much smaller scale, right? So I'm my PhD dissertation was on dark energy, structure formation in the universe, right? The very largest scales that we could possibly explore. And now I work on sort of like meters, right? My scale is meters and not, megaparsecs. So I think that my journey was quite similar to a lot of people. There is a bit of a diaspora. I mean, some of us went into statistics, some of us went into computer science, some of us went into, I'm maybe unusual in that I went into very humanistic questions. So I worked on natural language, for example, how people talk. But yeah, that was, I get this question sometimes, right? It's always funny. It's like, so, you have a PhD in astrophysics, what are you doing here? But there are a lot of us. And it was, yeah, I mean, not too many people became bitter about it, but certainly there was a sense that, at 17, 18, we were maybe sold a story that didn't pan out. And, that's nobody's fault. It is certainly really interesting. Watching, I don't know, I was rewatching Oppenheimer, and this idea, right, that you would, get on a ship and, show up in Leiden, and, Werner Heisenberg would be giving a talk. Like this was, that's not how physics is these days. It's a very different subject. But you can get on a plane today and go to a talk in the cognitive sciences, and it will blow your mind, and it's the most exciting thing you've heard all year. So, yeah, I don't know. That's a long-winded answer. Usually when people ask me this question, it's like I just say charm, because moving disciplines does require that you learn to listen and respect people. But there's a certain social intelligence you need to show up in a new field. Some physicists, I mean, all physicists are very arrogant, but yeah.
How do you think your physics background affects your work in humanities? I think there is also a lot of merit in devoting yourself to one subject and studying that in a very detailed manner. Yeah, of course, like a PhD is that you really devote yourself to one specific question, and then you deal with this for multiple years, and then you decide to switch into something different. So you kind of always have this kind of background in the topic that you initially studied, and then you, I guess, kind of also carry a little bit of the discipline that kind of shaped you in your beginning years as a scientist. In your future. How do you think this affects you?
I think, I mean, it's, in physics, right, the fundamental answer is very simple, right? The basic structures of a theory in physics are incredibly simple, right? They're essentially sort of almost axiomatic. And all the work is like doing the calculations, right? The objects are simple. It's very easy to take a theory like electromagnetism and produce incredibly complicated problems out of it. But at its heart, right, what you learn as a physicist is that the fundamental structures of reality are mathematical, and not just mathematical, but mathematically simple. I was talking recently, I was working with CMU is a kind of amazing place, and so I was working with a graduate student in philosophy. Our philosophers at CMU know a lot of mathematics, and so we were working on a theory called the information bottleneck. And, we were sort of chatting, and he said, well, why should we use this form of the problem? And I said, oh, that's just the most natural form. And he's like, what do you mean natural? And physics gives you a sense of naturalness that comes, I don't know what it means you sort of know it when you see it, but a natural theory is one that is mathematically simple, that has unexpected consequences, that obeys lots of symmetries. So that's that's sort of what drives me. Every morning I wake up and I expect that today we're going to find something that has a really simple explanation, has something that's mathematically extraordinarily elegant. So there's all these value judgments, right? And I guess that's right. You spend, I was in my undergraduate for 4 years. I spent a year doing applied mathematics, theoretical physics, and then 4 or 5 years in my PhD. Another 4 or 5 years in physics as a postdoc. So that's a lot of, you're learning how to do calculations, but you're also absorbing a certain kind of ethos. And that ethos is that the world is actually really, really simple, right? Almost bizarrely, like God loves us, right? To have made the world like simple enough that we can study it, and hard enough that like we can study it for centuries. So I think that's it. I mean, if I spend a lot of time now with psychologists, right? And psychologists come in to the same problem in a really different way. It's a really productive kind of discussion because on their side, some great psychologists are often narrative makers, right? They can always see another thing that layers on top, and yet another thing, and yet another thing, right? And so a psychological theory usually has 55 different components that are all fitting together. From the point of view of a physicist, this is extraordinarily ugly, right? Like you should never have a theory with 55 parameters. Physics like that puts me on the outside a little bit of my colleagues. But then there are plenty of psychologists and social scientists with a physics feel to them as well. I suppose that's it. Galileo, this is like the Galileo's story, right? The book of the universe is written in the language of mathematics, and that language is a very, very simple one. Simple in the sense that, it's like I say, very hard to do calculations, but very easy to express the underlying form in a succinct fashion.
So my next question is kind of about the layers of reality, if we can call it like that. So maybe this is sort of like the bridging question before we go to some more mathematical topics and topics that you're working on.
Mm-hmm.
It seems that what we call reality exists on multiple levels. So there is the physical world, but also perception, interpretation, and then we have this kind of symbolic system that we build, like language and mathematics. And what's interesting is that these layers don't just sit on top of each other, but they also kind of feed back to the previous layers. So the models we build can actually change the physical world. So do you think that this kind of makes sense of reality as something layered and recursive? Or do you think that this is a wrong way to kind of describe our perception of reality?
It's, there are many definitions of reality, or many, what's the word, folk definitions. There's one by, I think it's the science fiction writer Philip K. Dick, who wrestled with delusions. His novels are often about this very sort of fluid interface between the psychological and the real, the symbolic, the imaginary. Dick says, reality is that which, when you stop believing in it, doesn't go away, right? So, like take the police, right? This is a very elaborated social construct. The word police does not appear anywhere in the fundamental equations of reality. If I get pulled over by the cops and I stop believing in the police, that doesn't make them go away. They are still there, right? And I can't stop believing in like things that I really wish I could stop believing in, right? Cancer is real, right? The police are real. And yet at the same time, right, you point to this kind of odd thing, right? Like, I mean, they're not in the fundamental structures of reality, right? There is a sense in which if we all simultaneously stopped believing in the police, then they probably wouldn't exist anymore, right? There'd be guys in uniforms, but, you see this, of course, in at the end of World War II, all of a sudden, certain police stopped existing, right? Very quickly in many cases. This is, you struggle with, maybe it's one of the reasons I've been attracted to these transition points in human societies. We're very interested, we did a long piece a couple of years ago on the French Revolution, right? The French Revolution is this wonderful moment where certain things that were real stopped being real, and other things that had heretofore not been real became real. And so we can see the creation of a new reality, some kind of really fundamental change in the nature of human experience that happened, right? To be young was heaven. I think it was Wordsworth who said this about the revolution. So there is, this is a question. You think about it like a social ontology, right? When does something that's not in the fundamental equations of nature, when does that thing gain a status as a thing, right? When does it become a thing? That is, you might say that's sort of the heart of most social science, certainly most of political science. How do we create these new objects? Just because we create them, it doesn't mean that they have a purely fictitious existence. So, in one sense, you can think of this as layers, right? There's down here are the quarks, right? And next is the protons and the molecules, and you keep going up this. Somewhere up here you have, things like obligation and justice, right? So one natural way is to think of things just kind of building upwards, right? So that these more like the cops are, in some sense, only just protons. But there's another sense, of course, in which these higher levels do feed back down. There's a lovely, I think it was Sarah Walker, I think it might have been at Arizona State. She says, if you look at the evolution of the solar system over, my astronomy is not as good as it should be, right? Over the last 7 billion years, I forget how old our sun is. You look at the evolution of the solar system, right? For nearly all of its history, right? You have a little picture here, right? And everything is obeying Newtonian dynamics, right? Planets are moving around, dust lanes are condensing, right? Jupiter is sweeping up the asteroids, right? And then until very, very recently, when you start seeing these bizarre phenomena, right? There's a planet and a tiny little piece of the planet detaches and flies off into space, which has never been seen before. It is definitely in some sense, it's a violation of Newtonian gravity, right? When we send the Artemis 2 to orbit the moon and maybe one day land on it, that is a very, very elaborated social reality that is bubbling right back down to truly fundamental objects. So there is this feedback loop, right? I think it's the kind of reductionistic viewpoint that in the end, cops and universities and mathematicians are just bundles of atoms. There's something missing from that picture, and so that feedback between those higher and those lower levels is something that I think we don't yet understand. I think it's something that maybe when you're 80 years old, right, and you're looking back on a long career, maybe you attack this question, right? How is it that we start doing these very strange things? Sean Carroll calls it complexogenesis, right? How does the universe start doing these bizarre moves that they're not in violation of its fundamental laws, but there's definitely something weird about it.
Okay, and now we will move slightly towards math, but I have another slightly weird question. So, we never really experience perfect lines, infinity, or like zero thickness in real world. And yes, mathematicians across cultures converge on the same abstract structures. So if we speak just broadly, maybe you can tell us what is mathematics to you, and do you think that this convergence is best explained by our shared cognitive architecture, or does it suggest that mathematical structure has some kind of independence from human mind, or how would you attack this question?
This is beautiful. I mean, these are the debates we have in the lab a lot these days, right? I mean, do we ever? I mean, when was the last time I encountered infinity, right? I mean, one thing you might say is I encounter it all the time, right? Our best physical theories have infinity baked in, and baked in on a really fundamental level. There is, how do I put this? Say this in like the most shocking way possible, right? There is this idea that occasionally occurs to people that the universe is a giant computer, right? This is, I grew up in the Apple IIe era, right? Like very, old school machines. And even then, right, you start to think like, this computer, it has like a kind of liveliness to it. And I wonder what if the universe is just a computer? And some very bright people have like thought about this. Probably Stephen Wolfram is one of the most famous proponents, but I think this is a complete delusion. I love it. I think it's this is not a foolish thing to think, but I think it's fundamentally wrong. The universe is as far as our best physical theories tell us, our universe deals with infinities on a very fundamental level. Our machines don't, right? Our machines have a finite amount of memory. They can count only so high. They can only store so many different configurations. The number might be very large, but so if you think the universe is a computer, you think that actually there are no infinities, right? You think that, for example, if you zoom in enough, you'll start to see a graininess to the universe. And we don't. I certainly spent my time in that world. But the one thing I might say is, just before we begin the meat of your question, which is a really good question, is you might say actually we experience infinities all the time. Electromagnetism, the light coming through my window here and bouncing off this copper plating, right? Our best explanations involve, in a really basic sense, the use of infinities. Infinitesimals, things that are infinitely small. Limits, things that go on infinitely long, or series that converge and only in the limit of infinity. So you might say actually like we swim in infinity, right? We have a great deal of trouble thinking about it, right? So the invention of infinity is itself like a kind of massive human achievement. We don't really, Aristotle has a notion of infinity. We don't get the analemma sign, like the 8 that's fallen over, right? We don't get that. I think that was invented in the Enlightenment. I believe this was a gentleman called John Wilkins who needed to come up with like a language of thought, and he needed the sign for infinity. So I guess he just took the 8 and put it on its side. Maybe it's like an Ouroboros, a snake eating its tail. So it's hard for us to grasp. But the first thing I might say is that, well, actually, our best theories suggest that, like, without infinity, things would break down, right? Or the world would look very, very different. So first thing I might say. Then the second thing is, when you look at the history of mathematics, one of the reasons we study it, of course, is that it is absolutely transcultural. The mathematics, the mathematics someone does in Montana and the mathematics someone does in Mumbai, like, these two people can talk to each other, without a hitch, right? The philosophy one does in Montana and the philosophy one does in Mumbai are very different, right? It's going to take a long time for those two philosophers to start to even get traction on each other, and there's going to be a lot of debate and anger about things. But mathematicians, like, this is, in a funny way, our universal language. And then the question is, well, where did that come from? Right? We see it every culture that survived, the Aztecs did not survive, right? We don't know what they would have done. But every major culture, every cultural tradition has mathematics and the experience of mathematics baked into it, right? We have like algebra, it's like al. It's from the Arabic, like I believe it means the simplification or the method. At 400 BC, we have the square root of 2, and all the cultures are trying to calculate it, right? You have a square, right? You have the diagonal of a square that's 1 by 1. What is the length of that thing? It's a weird thing, right? It's like, it's bigger than 1, and like, it's like less than 2, and it's somewhere, like, what is this thing, right? So we've encountered these objects, cultures encounter them. You don't super need them, right? Because humans have such problems with infinities. Like, if you just want to do accounting, you do not need infinities, right? If you want to do interest rates, like, you do not need infinities because, like, you just do it day by day. Like, you don't need the exponential function. That's something that only occurs to you if you want to do infinitesimals, right? So in one sense, like, this is this universal, and it's a real puzzle where it comes from. But there's another kind of odd feature to this. So when you look in the history of mathematics, there was essentially only one culture that developed the notion of mathematical proof, right? So you might say there's two kinds of mathematics here. One is applied, it's what I trained in, right? Applied mathematics is like, I don't know, man, make it work, right? There's another notion of mathematics, which you learn when you do Euclidean geometry. The first encounter in most places is proving things about isosceles triangles and, you drop the perpendicular and you find where they intersect, things like that. That notion of proof, as far as we know, like, it emerges once, right? At least the only record we have that survived is it emerges once, off the coast of Turkey on the island of Samos, right? With the Pythagoreans. And so, like I mentioned, the square root of 2. So the Greeks were actually technologically the Greeks were not great, right? The Indians, the Indian civilization, like the Hindu civilization, they knew the square root of 2 to more digits, for example. They had a more accurate notion of what it was, right? 1.4 something, right? Although they didn't use decimal notation. The Greeks, however, had this kind of crazy thing, which is that they proved, right, and what is a proof? It's a good question. They proved that the square root of 2 was irrational, meaning you could never write the square root of 2 as the ratio of 2 integers. So this is really, this is huge, right? This is a major step forward. You might say it's our first encounter with a certain kind of infinity. The irrational numbers there are more irrational. There are infinitely more irrational numbers than there are rational ones. That's something that took us a long time to figure out. But it was the Greeks who figured this out, right? Or this particular civilization sitting there in the Aegean. So, I wonder this. I think a lot of people, what was it? What was in the water at that point in time that gave us access to that, right? It's completely useless for calculation, right? You're trying to build the pyramids. The Pythagorean theorem helps, right? But you don't need, like the fact that the square root of 2 is irrational is irrelevant, right? You just need a good approximation, and you don't care that it's only an approximation. That it never occurs to you. But the kind of mathematics that truly is transcultural is that kind of mathematics. And that seems to emerge, as far as we can tell. Like I say, the Greeks were not particularly technologically advanced. There wasn't like they didn't have. I mean, look, the fish was good, right? But it wasn't like they had access to coal, right? And other civilizations didn't. But maybe what they had was a particular social organization, right? So they had, like every culture, they had an interest in numbers, right? They were interested in them. But not only were they interested in them and what these numbers could do for you, but they also had a culture, at least among the elites, they had a culture of debate, right? So they had a proto-democracy. It's in one sense, it's kind of wrong to call it a democracy. They would themselves not have called it a democracy. But they did have a notion that if you were at a certain level in that society, you sat around and you made arguments to each other. And so you almost want to say, like, what happens at this particular point is that the argument-making impulse, the sociality, right, interacts with this sort of mathematical number instinct. And it just so happens that at that point, right, these two things collide, right, and we get the kind of mathematics that actually cares about perfectly straight lines and perfectly round circles and perfectly infinite or infinitesimal quantities. So it's an odd, like, let you meet space aliens one day. Will they have a notion of infinity? Absolutely, because you can't get to space without a notion of infinity. But then you say, where did it come from? Was it baked in? Was it baked into their cognition? Well, in some sense, it wasn't baked into our cognition, because we went for, how many tens of thousands of years, and we never did it. And then when we finally did it, it only happened in one place, right? It only, like, we figured out, like, cook your meal is something that every culture figures out at some point. Like, meat tastes better when it's cooked, right? Love, like, poetry, novels, stories, music, different scales, but we all got music. But for some reason, like, this was a rare discovery that just so happened to have occurred at this one point, and then of course spreads, right? And it spreads because for some reason that combination is not just extraordinarily powerful, but it's extraordinarily exportable. So once you have Euclid, right, Euclid, like, disappears from the European continent for a long time, right? And it's brought back to us, right? These texts come back to us via, at least for the Europeans, via the Arabian Peninsula. So there's something really, like, that story of mathematics, right? The first question you want to say is, okay, where in the brain do we keep our circles, right? And why would we ever have a circle part of our brain, right? Let alone straight lines. That's the first question. And there's, you might say, okay, we have edge detectors in our brain. Maybe we like line, but there's a second part of it, which is that there is a social activity here that we have. That social activity is constitutive in mathematics. Like, I'll give you I can go on about this for a long time. It's fascinating, right? Like, take the Europeans in the year 1200, right? In the year 1200, they can do calculations. They're obsessed by the date of Easter, right? Because we had this split in the church, right? So for some reason, we got to calculate the date of Easter. It's a lunar calendar, but right? Like, how do we do this? And so they can do really sophisticated calculations, but they've lost that Greek tradition at that time, right? They don't have the necessary social technology. So what happens, right? In 1250, right? You still have all the math nerds. It's sort of a sad thing, right? You have all the math nerds. There are math nerds in, 13th century Europe, but they don't have that social technology to exist within, right? So they have certainly, if you could take one of these people out, right, and we can find, I'll tell you in a moment, we find them, right? Imagine taking one of these people out and you drop them in, 1950s, like Berlin, right? Maybe not Berlin, drop in 1950s, like Moscow, and they would catch on really quick. They'd be like, I found my people. But at that point, we had lost it, right? You drop them, you rewind in time, take them back to the Pythagoreans, they'd have a blast, right? So, we have these great manuscripts of, like, what does a math nerd do when they don't have the social tradition to go along with it? And, like, they do some math, but it kind of goes off the rails, right? They want to talk about infinity, but they don't have enough people to bounce the ideas off of. They don't have the notion of proof or they think they have a notion of proof, but they don't really, right? So there's this social component seems really critical to, you know, this achievement of, yes, being able to think about infinities. If that was irrelevant or just icing on the cake, I mean, first of all, we would be a lot further along, right? But it seems like you do need a functional society in order to have functional mathematics, right? You do need a community of mathematicians. You do need, like, you know, they don't need much else, right? If you look, like the Simons Foundation, for example, funds a lot of mathematics. And if you look, like, what does it mean to fund mathematics? Like, do they need more like, they have enough pencils are cheap. Mostly what the Simons found, they don't really need computers, actually. Like, I mean, it's cute, right? But you don't really need a computer. In fact, many mathematicians don't use them. Although this is, of course, changing. It's changing very rapidly right now. But most of what they do is literally just buy people plane tickets, right? Like Airbnbs and plane tickets, because, you know, if you want to think about infinity in a certain kind of bizarre way, and the only other guy who thinks about infinity that way, like, she lives in Berkeley, like, you gotta go to Berkeley, right? So, like, the grants are tiny. They're like $5,000 to, like, just get you to Berkeley for, you know, a month or two. So I think that's part of it. I mean, you asked this question, you know, circles, perfectly straight lines, infinities, we never encounter them in reality. I mean, I say in one sense we do, but not really, right? Like, you need a PhD in physics before you can really truly believe that we encounter them on a daily basis. But the fact that we can wrestle with them is, you know, at least as far as I can tell, is in many ways a social achievement just as much as a cognitive.
I completely agree. And before we go on to talk a little bit about proofs, I do think that a lot of social structure and culture is really important to share the knowledge, and really depends in what kind of political system people exist to be able to share knowledge. Or I mean, throughout the years, I think it is also quite interesting to
Mm-hmm.
maybe look back, and you also think, in the time of Enlightenment, if I am correct, there was a lot of people who did a lot of things across multiple disciplines. So let's say a lot of polymath.
I think I mean, you bring up a lot of really interesting questions all at once, right? So, um, mathematics requires sociality, right? The Russians, Soviets, right? Really great at mathematics, truly great, right? Um, you know, one guy, Kolmogorov, right? Like, you know, because of the Iron Curtain, right? You have mathematics in the West and you have mathematics in the Soviet Union, and there's not a lot of contact, right? Eventually, finally, word gets out. And, you know, we discovered the Soviets have, like, replicated all of our mathematics, and it's like with a smaller number of people living in, like, quasi-starvation police state conditions, right? And it's like really humbling and really stunning. And so then you say, well, why were these mathematicians so good? One answer is actually that if you had a soul in the Soviet Union and you had a brain, right, like, that was all you could do, right? Like, there are no philosophers in the Soviet Union, right? Or there are no great philosophers in the Soviet Union. Don't kill me, right? I don't know, Bakhtin maybe, right? But, like, they're either always getting arrested or they're writing kind of dialectical materialism bullshit, right? So if you wanted truly free thought, that was the place you could go, right? And the Soviets were smart enough to realize, you know what, good mathematicians, like, there's probably some bomb angle on this one, right? So they kind of let them be roughly free. As you know, you had to occasionally denounce somebody, right? So one thing is, mathematicians, like, mathematics requires sociality. It's also a bit of a covert thing. You mentioned the Enlightenment, right? You know, the Enlightenment was a really dangerous time, right? So I'm sitting, actually, you can see just in my back here, a gift from an old friend is this, right here, this is Descartes', it's like the 1640-something edition of his geometry, right? And it's published in the Netherlands, right? Why are you publishing the Netherlands? Because this stuff is so radioactive for the French at the time, that, like, you know, this was dangerous stuff. And so that, like, in one sense, mathematics can fly below the radar, right? It's a place for people to formulate ideas under conditions, in one sense, of complete freedom, right? but they can formulate ideas that in strange ways can be unbelievably radical. So by the time you finish, studying enough geometry, you end up the other side, you come out like an atheist or a monist or something, right? So that interaction it's a really interesting one, right? Mathematics in some sense is extraordinarily fragile, and in another sense it's extraordinarily robust, right? Mathematics is far more fragile than poetry, right? I don't need a huge education to enjoy Yeats, right? Like, you read a Yeats poem, Yeats is just amazing, right? Civilization ends, we're sitting around the campfire, somebody remembers, a little fragment of, sailing to Byzantium, right? And we all love it, right? It's great, right? Mathematics is much more fragile, right? Without an elaborate university system, without the funding to support, they don't want a lot of money, but you need some, right? Without a university system, in the modern era, without open borders, so people can travel freely, that you can get the best people to the best places. It's a very fragile system, but in another sense, it's really robust, right? Because once you have something there, right, other things can happen. So mathematics, secretly, one of the reasons, look, mathematics is beautiful, ex-physicist, so of course I'm going to respect mathematics, but it's also a bit of a test case, right, for the nature of really difficult thought, right? What happens when people think really, really hard, and in some sense think really, really hard without constraint, or without the constraints imposed upon them by the wider society? They're constrained by, let's say, the laws of deduction, they're constrained by the nature of proof, but beyond that, there are no constraints. The only other constraint is how hard can you concentrate? So it becomes a really interesting, it becomes a really interesting social phenomenon where, you might say mathematicians are the most specialized, right? There are 10, if you're a mathematician, there are 10 people who understand what you do. It's really hard. When the New York Times does does an article about a psychologist, it's really easy to understand, right? Mm-hmm. You can get the meat of their discoveries in a New York Times article. If somebody proves a major theorem, the New York Times basically has to vague gestures, right? It's beyond all but the most specialized people. Yeah. So in one sense, it's very specialized. In another sense, though, it is the sort of anchor point for all polymathic behavior, right? The Enlightenment was a moment where you had, Isaac Newton is writing about the Bible, right? Spinoza is writing about ethics. Leibniz is writing about anything, everything. Descartes, right? So in one sense, the Enlightenment it seems like a complete free-for-all. But in another sense, all of these people were anchored in the experience of mathematical proof and proof-making, right? They weren't great storytellers, right? The Renaissance, the literature is better in the Renaissance, right? Shakespeare and Dante are way better, Enlightenment literature. I guess there is some, right? And I'm going to remember it after this podcast and feel terrible because I'm sure there's great Enlightenment literature. But it's let's go see some Shakespeare, right? I don't know, Alexander Pope. I don't know who's writing in the Enlightenment that we care about. They weren't great storytellers, but they were obsessed by, and they got this from the mathematicians, they were obsessed by this notion that you could make progress, that you could discover things truly new, through this method, right? Through this method of proof making, which is, what is it? Well, ask Pythagoras, right? It's some thing where you put your cognitive capacities in contact with public debate in a certain way, then you get, right? So there's, in a funny way, you might say that the most specialized of subjects, mathematics, is the anchor point for the most general of minds, right? Without that notion, you can't talk about infinity. Take, for example, these 13th century people who, the math nerds before math nerds had a home, right? So there's one that I'm working with a faculty member here at CMU in the English department, Seth Strickland. So Seth is like, check this out, right? This is this guy, Richard Grosseteste, right? He's the bishop of, I'm going to forget, Lincoln? He's like in Britain, right? He somehow maybe got some Arabic manuscripts. I don't know how he can read them, right? He wants to talk about infinity. And, he's got to squeeze it into, text about Easter and the date of Easter. He wants to talk about infinity. And you can be like, this is not it, right? Like, you have the brain power to do this, but you're just writing science fiction, right? You're writing, 13th century science fiction. Whatever Leibniz and Descartes are doing, they're not writing science fiction, right? They are doing something. Is it science yet? Hard to say. But they are able to do something that, Grosseteste couldn't, right? Grosseteste was still in this narrative era, this era of declamation, not the era of what we might think of as true, socially tested argument making. So I know it's a long-winded answer. I mean, it's a beautiful, this question, right? Of course, like, we all want to be polymaths, right? We all want our hobbies to be our sciences and vice versa. And you're right that the Enlightenment was that point, right? I mean, we say Renaissance man, but really what we mean is Enlightenment human, right?
Yeah.
It was the Enlightenment that produced the ideas and the texts that we now think about, right? If you scroll back, you have Montaigne. These are more kind of psychological narrative. They're on the cusp, right? You can see that somewhere in the future there's going to be something, right? But they're not there yet. Right, they're educated, but they don't have this like critical method.
Yeah, this brings up a lot of different questions now for me to ask.
Well, yeah, well, go ahead. No, but yeah.
But I think I will go how do people in the community accept proofs? So we often think of the proofs as this kind of purely formal objects, sequences of logical steps, but they also need to be understood and accepted by a community. Mm-hmm. So, at what point, because in maybe in the next question, we can also discuss how this relates to AI and how then AI, now lots of large language models can do proofing, and it's not necessary that this is understood by people.
Yeah. Things are getting really weird. Yes,
yeah.
They're getting very strange. No, this is. I mean, we're. There's a reason I'm doing what I'm doing, right? We are in a moment that is. I would say this is the biggest moment in mathematics since Descartes, right? Since, algebra, since Descartes brought algebra and geometry together, don't hold me to whether he was the true origin of it or not, but we are in a very, very strange, exciting, dangerous moment because proofs are escaping us, right? Mm-hmm. So you're right. So the history of the 20th century is proofs become increasingly elaborate and difficult, right? Modern mathematics, like maybe, after Hilbert, right? Mathematics becomes stranger. It becomes much more specialized. I mean, you had specialization in the 19th century, but someone like Poincaré could reasonably be said to kind of have a grasp of most of mathematics. That's no longer true. The best mathematicians alive today will never say this, right? They, mathematics ramified, spread out, the problems became deeper, right, in both senses, both semantically, like these are deep, really fundamental questions about the nature of mathematical reality, but deeper also in the sense that you've got to go down a hole and, if you're not in the hole, like, it's really dark down there and you can't see, right? If you're in the hole, you look up and you see the light, but when you're standing at the top and you look down, like, it's dim and very obscure. So, proof making became something, and you might say crisis is the wrong word, but our proofs became more specialized, more elaborate, less easy for outsiders to understand, The famous case is Wiles's proof of Fermat's last theorem, which required an enormous effort by the referees, right? I sent a paper in to the journal, and 3 months later, I get yelled at by referees, but they get it, right? And they either figure out the problem or they say, hey, not bad, right? But in mathematics, the referee process, understanding the proof has become so hard that we've begun to lose control of it. There are some examples of famous mathematical proofs, or rather not so famous mathematical proofs, that looked okay and were built upon by other members of the community and were just wrong, right? They were wrong either because they were false, meaning they, like you said X, actually there's a counterexample, or they were wrong in the sense that their argumentation structure made an assumption that you could prove was wrong. So whether or not the theorem itself is true or false, who knows, but we could tell that this particular proof, there was a very subtle error here that, it happens. Why? Because, speech is slippery, and even mathematicians, they speak as carefully as they can. They will still slip, right? Mm-hmm. So that's where we were. Machines get more and more powerful. They get more and more we're able to use them in ways that are, they require a lot of computer power, but we can start using machines to mimic mathematical reasoning. So the first stuff in this line was done in the 1990s. It has a long history of machines that can reason. It goes, Leibniz, it comes up with this idea. But to actually make the dream, right, to take science fiction, make it reality, at some point we start developing programming languages that hypothetically, if you write a piece of code in this language, it's equivalent to writing a mathematical proof, and then you just see if it type checks, see if the code compiles, and if it does, and it runs, the theorem is proved. This is it's very weird, right? This analogy between writing a mathematical proof and writing a computer program, it's been in the 60s, people sort of started to notice this, right? But it wasn't until the 90s and 2000s that machines got powerful enough that we could make that analogy real, that we could actually start proving things. And so, in the 2000s, some people, including people here at Carnegie Mellon, like Jeremy Avogad, they were okay, let's prove reasonably advanced theorems that an undergraduate would encounter in these new languages. And we can prove them, meaning we can write a piece of computer code that we believe corresponds to the human proof. We write that piece of code, it compiles, and the machine says it's true, and somehow we think this is working. That world expanded. It became like a lot of things. Once the internet switches on, a lot of people start working on this, building on it. We end up with these languages like Lean. There's another one called Rock, Isabelle. These are all languages that, in some sense, are languages that are sort of formal versions of a human's English or whatever, Russian or Chinese language proof. Mm-hmm. So that's sitting there, right? And it's some people like this, some people are like, oh, that's cool. Other mathematicians are like, that's cute, right? Other mathematicians are like, I hate computers, right? We have these languages, and then the next thing happens, which is these LLMs switch on and they start writing code in these languages and they start proving things, right? And this is really bizarre. The example I give is, if you're a college professor at this point, right, you're dealing with your students sending in AI-generated work. I don't have that problem for interesting reasons, but a lot, if you're teaching a class on Dostoevsky, right? You're teaching Dostoevsky and it's okay, write an essay about crime and punishment, right? And, ChatGPT will write me an essay on crime and punishment, right? I could say, I give this example to my friends in philosophy. I was like, look, hey, computer, argue for Plato's theory of forms, and it will generate, a 7-page argument in favor of Plato's theory of forms. And, you say, who cares, right? Is that a good argument or a bad argument? Probably not a great argument. It's sort of pointless, right? But you can tell a machine, prove this theorem, and it grinds away, and out the other side comes this object, that it claims is a proof of the theorem, and you run it through the type checker, and the type checker says, actually, yeah, like, that theorem is proved. And so this is really different, right? Like, the philosophy paper, it's like, yeah, you wrote another bullshit paper about Plato's theory of forms, but it doesn't really advance our knowledge of philosophy, because what kind of argument is it? It's probably a mishmash of things we've all heard before. But in the mathematical case, at least you could say it's a valid argument, right? And you can check it. Like, we're running, actually, while we're talking, we're running stuff. We have a supercomputer center here, the Pittsburgh Supercomputer Center. It's currently producing, well, I don't know, let me look, right? It's got like 357 proofs of like the Ein-Borel theorem, right? Which it just proved autonomously. And when I say 357 of these proofs, right, I mean that like these are proofs that are valid, right? And it's proved it in 357 slightly different ways, right? We've never seen this before. We've had, you know, since ChatGPT turned on, we've had machines that can like imitate human language, but we have yet to have machines that can do something new, meaning advanced knowledge in some way, right? Now they can, and they're doing it, and this is really strange, right? If you go back to 1960, 70, 80, 90, like mathematicians, their entire job is to produce proofs, and these proofs get weirder and stranger and harder to check, right? And we're at a point now where machines, and I think most mathematicians who have thought about this are pretty convinced that this is going to happen, that within 10 years, machines are going to be proving theorems as a matter of course. And they're going to be proving not just theorems we've already proven ourselves, like Ein-Borel, we have proved Ein-Borel a million times, right? Every, you know, like upper level undergraduate class in analysis does it, but the machines are now going to be able to prove things that humans have not been able to prove. So if mathematics began with proof, right, if that's the origin, right, if it begins with Samos, right, does it end here in Pittsburgh? Obviously it can't end, but we don't know what is going to happen next. We really don't, because first of all, the codes these machines are producing, again, we know it's valid. We know that I have more confidence that this machine has 357 valid proofs of Hein-Borel than I would be if I had 357 undergraduate exams to grade. But somehow, I don't know, somehow the things we thought mattered are out of the equation. The machine doesn't talk to anybody. It doesn't argue with another machine. I mean, you can set up these little games where it argues with itself, right? But something really, really bizarre is now happening, and we just don't know, right? We don't know what it means. Like Tim Gowers, great mathematician, he's in France, he's a Brit. Tim says maybe, you know, in the future the job of mathematicians will be to understand mathematics as opposed to prove theorems. But every mathematician right now still thinks of themselves as a human who proves things. And Tim says, well, maybe that's not going to be our job anymore. Maybe our job will be different. I don't know what that means, right? Like, no one thinks philosophers are going to be out of a job for some reason, or that somehow philosophy is going to have to fundamentally change. But the mathematicians certainly believe this about their own field, and I think they're not crazy to think so. And that's been the energy. The other thing that's crazy, of course, is, you know, okay, why is anybody giving us money to prove theorems, right? Given how useless mathematics is. You know, go back to earlier in the conversation, like, you don't need to know that the square root of 2 is irrational to build a building that doesn't fall down. In fact, it's totally irrelevant to building a building that doesn't fall down, right? So why are there hundreds of millions of dollars flowing into this? Well, there's a second thing, which is that if we can get machines to prove theorems, at least we know it's not a hallucination, right? If I get the machine to write 357 essays on Plato, I have to check them to see if it's hallucinated quotations, it's hallucinated points, right? It's hallucinated arguments. These I know are real. So all of these big AI companies, they've chewed through all of our data, right? They've eaten every single Reddit post that's ever been made. They have chewed through every book that's ever been published, right? They're scouring the secondhand bookshops to find anything they've missed. But we're running out of human data, right? Like, it has consumed nearly all of our data. And so what's next, right? And so the idea, I believe, and this is something that floats around, I'm not involved in the commercial aspect of this, but the idea is that if a machine can start producing proofs, it can now start reasoning autonomously and can go beyond the humans. So there's an idea that this activity that in one sense is the beginning of advanced civilization, right, is also the place where it's the beginning of the advanced machine, like the truly advanced machine civilization. So this is a strange moment for us to be in, where, I don't know, it sort of kind of wraps back around, right? The discovery of the irrationality of the square root of 2 was a moment, right, that in some sense, if you look at the great moments in human history, that's one of them, right? Monotheism is one of them, right? Like legal codes, right? But these are like iconic achievements, and now the machines are getting there as well, right? When our machines prove Heim-Borel, it's a bit of a cheat, right? Because there's a lot of text about Heim-Borel out there. But when a machine starts to produce novel proofs of things that we have never proved before, which it seems like it's getting there, this is where the next phase transition in human civilization is going to happen. I don't know what's going to become of us.
So how exactly this would then work for people entering into the field of math? Would then this kind of like lower the threshold or up the threshold? I have no idea.
If you talk to young, this is a really good question, right? Because it is also a bit of a crisis. There are a lot of people. It is incredibly dispiriting at first if you're a young person in mathematics. You love mathematics. Mathematicians don't go into mathematics because they like computers. If they like computers, they go into physics, right? But you love mathematics. You want to swim in the quaternions or whatever it is you love to do. And then some asshole shows up and says, "Oh, we got a machine that's going to outrun you. That's going to prove these theorems first," right? Because everybody wants, currently, the way you do mathematics is you are the discoverer. You are the first person into this new field of reason, and you have planted the flag, and you have discovered, here is how to prove it, right? There's a book called Journeys Through Genius. It's a beautiful book, actually. I read it years ago. And it just does different proofs in mathematics, right? It does Pythagorean theorem. It goes up to the uncountability of the reals. Beautiful. But it's, the iconic moments or the iconic proofs. And so if this bizarre future that Tim Gowers and many other great mathematicians think is plausible comes to pass, it's a very exciting, it's like being a lawyer during the French Revolution, right? What does it mean to be a lawyer when all the social structures around you are collapsing and getting replaced? In one sense, it's the most exciting thing of all time because you're the person who can understand what that even means. And at the same time, you're so this is a very, very strange moment. It's an exciting moment. It's the opposite of what it was like when I was a grad student in physics. Man, we wished that there would be some crazy crisis in physics, right? So we could come to the rescue and bring our youthful energy and enthusiasm and ideas to it. I guess, the mathematicians now have that problem, right? They're living in the most exciting time that their field has seen, I think it's plausible to say, since Descartes, right? It's not, this is not a once in a century thing. This is like a once in a millennia event for mathematics. And one answer is to become really super depressed about it. Another answer is to ignore it, which is, by the way, a totally legitimate thing to do. Most mathematicians don't really know about these things. They encounter them if they read about it in the newspaper. We are losing faculty, so mathematicians are leaving the university to go work in these AI companies. We heard a rumor of a mathematician who got a job offer from one of the AI companies and was like, I have to finish teaching the semester. And the company said, if you don't leave right now, you lose the offer. So he ditched his class, which is absolute academic malpractice. If you're a doctor, don't leave your patient. If you're a professor, don't leave your class. So we are losing some people. I don't know. I'm in America, right? Everything's going to be fine, right? But it is certainly a really very deeply strange time. And because it's such a strange time, you can be an optimist, you can be a pessimist. be a nihilist. Like, it's not quite clear what's going to be on the other side.
Exactly. And now we are slowly approaching the end of the podcast. So maybe one or two final questions. Let's see how much
Go for it.
how much
Hit me. Yeah,
we
this is great.
can
Thank you, Tanya.
squeeze in the next couple of minutes.
Yeah, perfect.
So do you think that so this is stepping away from, well, kind of stepping away from math, but do you think that the way societies create meaning is fundamentally similar to the way math creates truth?
It's a loaded question. I mean, the natural answer is no, right? I mean, this, very clearly, the meaning making or the truth discovery that happens in mathematics, like, it's a skill. You've got to learn it. I'm not very good at it. Like, I've tried to prove, like, I can't do it. I like to think that I'm otherwise reasonably good at meaning making. I think a deeper answer is that when a mathematician discovers an object, like, since it came up earlier in the conversation, the notion of infinity has been floating around for a long time, right? Like, I mean, let's say Aristotle has it way back in the day. It sits there, it's being used, we are using it to make arguments, but it's very clear that we don't understand it, right? And over time, we start to put anchor points in it, right? We start to understand what's the limit, right? What's the limit of an infinite sequence, right? We start to understand, okay, are there different kinds of infinities? Like, here's one infinity, here's another infinity, right? This notion of cardinality, right? And one-to-one matching that Cantor gives us. The modern era, like, the notion of infinity gets into metamathematics, provability, like these things called large cardinals. So in that sense, right, we have this thing, this notion of infinity that over whatever it is, 2,500 years, we increasingly enrich, right? And we enrich it mathematically by saying true things about it, we so hope, right? The theorems of, infinite sequences, these are true statements that we establish through deductive proof. So in that sense, there is a really nice analogy, right? I mean, you might say we discover, we put, like, the meaning of justice, the meaning of love, the meaning of, like, life is an unfolding object, right? We can see, like, when we say, oh, like, look at Christ, or look at the Stoics, or look at the Enlightenment. These are people who are taking notions that have been floating around for a long time, and you might say, saying true things about them in a way that enriches our notion of the underlying object, right? Like, we live a more meaningful life because of those behaviors, those actions, those discoveries, those stories, those, historical events, right? That gives meaning to these concepts, right? We have a notion of human rights that we get, like, in one sense it starts at the French Revolution, but there is a prehistory to it, and there's certainly a history afterwards, right? That notion is, and depends how, spiritual you want to get, right? That notion is something that we unfold over time. And if you look at mathematics, yeah, we keep discovering. I mean, you might say Pythagoras discovered something about the numbers, right? There were these holes, right? We thought we knew the numbers, right? We thought we knew what justice was, and then, lo and behold, we discover something, and once you see it, you can't ignore it, right? The French Revolution, like, they freed the slaves. I mean, then they undid it, right? This was a very clear moment of discovery that's very hard to, like, undiscover, right? And in the same way, like, Cantor reveals things to us about this notion of infinity that we can't unsee.
What do you think we still kind of misunderstand about humans, how humans create knowledge and understanding?
I mean, in one sense, you're asking what are the puzzles, right? What are we missing?
Yeah.
In one sense, we're missing a great deal. I used to work on Wikipedia, right? Remember Wikipedia? And it was like this encyclopedia, and it's still there, and it's great, right? And, it's a very interesting social system. So a lot of us were studying it in its early history, figuring out, like, how the hell did it work? And we had all of these theories. And the joke people had was that Wikipedia works in practice but not in theory, right? Like somehow this system just worked, and yet we had no good theory for why it worked, right? And we were all trying to figure out like what was the underlying explanation for this. And you look at the arc of human history, the fact that we are able to do mathematics, like I wouldn't have predicted this, right? Like I would not have predicted the insane complexity of our civilizations, right? I would not have predicted the achievements. I would not have predicted that we would go to the moon, right? Of course, like there's nothing mysterious. We went to the moon. How did we do it? Like JFK had a thing, right? We had some Nazis, we needed to, historically it's not a mystery how we went to the moon. It's physically it's not a mystery, right? We have the chemistry to do it. But if you sort of transport yourself back, you look at human civilization 20,000 years ago, such as it did not exist, right? And you might be like, yeah, I bet you guys are going to get writing. I can sort of convince myself that writing, double entry bookkeeping, some of this stuff, very predictable, right? But a lot of it to me seems like an enormous mystery, right? And again, it's one of these things like Wikipedia, of course it works, what's the problem? But when you actually try to figure out how all these people, just random strangers on the internet, wrote an encyclopedia that put every encyclopedia company out of business, and not only every encyclopedia company, but every competitor, right? Everyone thought they could, nothing worked, right? I don't think we understand. I don't think we understand the origin of these long tail events, right? We don't understand how we can get a proof of Fermat's last theorem, for example, right? You're asking. It's funny. You're basically asking me tell me what you don't understand, right? I can't explain it. I mean, if you were to say, you put a gun to my head and say, explain how we could do Fermat's last theorem, I'd be like, oh, you have these exceptional cognitive performers, and you put them in the right. But it's a little bit like saying, how do we get life? Oh, you get the right molecules and you put them in a soup and zap it, and it will happen, right? But I think that's kind of where we're at, right? It's a little bit like Origin of Life, it's one of the hardest problems and it's one of the easiest problems. Obviously it happened, right? But how did we get to a point where we could do that proof, right? Yeah, I mean the natural instinct. I mean, in this field, when you study mathematicians, right, the natural instinct is sort of cult of genius, right? And yeah, there's no question that Andrew Wiles and his collaborators and the people who verified the proof and that whole world, they were, they could concentrate, right? They could probably, do, if I read them 7 digits, they can read them in reverse order without mistakes, right? But I can't figure it out that, and I think it's a problem that sort of sits there really obviously. A lot of social science and psychology is a bit like this, right? Political science, what is political science, for example? There's great political scientists, but you want to grind out a paper, right? In political science, one thing is voting behavior. Why do people vote the way they do, right? And there's lots of theories, right? Mm-hmm. But there's not a lot of we don't really know how do we have voting at all, right? You might say it's more pressing in political science because we also ask when does voting stop, right? When do democracies die, not just when do they emerge. But yeah, I think those, in the stuff we work on now, it's how is that possible, right? How is that achievement possible? How do you get? I mean, part of it is just raw intelligence, I suppose. I don't know, but we've had raw intelligence for a long time. Right, and it kind of didn't go anywhere, right? We had really elaborate sections of the Talmud, right? We had really unbelievably complex polyphonic compositions, but it didn't reach this insane behavior that we see in mathematics. So I think that's the mystery, right? The mystery is not how do I put this the right way? There are lots of great open questions in how do children learn to count, lots of great open questions in how does an average person reason logically about something or other. But what we don't have a handle on, and we don't even know what the right questions are to ask yet. I mean, I feel like we do in the lab, but that's a separate thing, right? We're trying to make the case. But what we don't, like, how do you get that extreme behavior, right? How do you get to those really extreme achievements? That, I think we don't know, right? You can't, I mean, if you ask, like, how can somebody run a 3-minute mile? There's biology, there's a little bit of social behavior involved, perhaps. But this stuff, that's a mystery to me. Those really extreme achievements.
For the very final question, do you, if somebody is further interested in the research that you do, where would you point them? Or maybe for the very last one, you can also tell us perhaps maybe what would be a good book or a good article that would kind of lead somebody into the topic that we have been discussing today.
Into the questions. So, yeah, I mean, so we got very lucky. We're funded. We got some funding from the John Templeton Foundation, and so we're able to do, like, this is the question we're attacking, right? People can go to our website, proofsandreasons.io, and so we're listing, our first papers are coming out on this. You know, are there great books being written? One of the things I have to do is write this book, so I promise to write a book on these questions. The mathematicians are talking about this a lot. We had a meeting at the Fields Institute back in 2022 that turned into 2 volumes in the Bulletin of the American Mathematical Society on the AI in proof. So that's one thing we've talked about in this conversation. The history of mathematics is a really interesting subject. The book I really love is by the author Robert Bella, Bellah, on the axial age. And he talks a lot about these kind of major civilizational moments, and one of the major civilizational moments is, in fact, the Greeks and the discovery of mathematical proof. So I think Bella is probably, for people who are interested in that kind of historical moment, I think Bella's really, really good. He has a very polymathic view because he's also able to talk about the parallel developments in China and India, in the Hebrew civilization that are happening simultaneously. One of the things he says about the Greeks is they had this mathematical notion that is absent, or at least much less prominent than it is in the other civilizations. But there's a lot there. We are well funded. We've been able to hire really good people, but in the coming years, we're hopefully hiring more people. We're hoping that more funding will come in. We don't build machines, right? We're not a pipeline into industry. We're asking these more foundational questions. But I think people are realizing that these foundational questions are actually really important. They're important partly because, maybe they'll help us build better machines. I think that's one thing. Help us control those machines better. But they're also important because, these are really profound questions about our species. So we're hoping the Survival and Flourishing Fund has given us some seed funding as well to kind of increase the scale of the project, to bring more people in. And if that happens, proofsandreasons.io is where you can go to find out more. So, Tanja, this is like a really delightful conversation. You've let me rabbit on for 90 minutes, and it's really, really delightful.
So I will say thank you very much for joining us today. And to our listeners, we hope that you enjoyed this episode with Simon DeDeo. And thank you very much for joining.